Live from Syosset, it's AP Course 1. How's everyone feeling today?
Awesome, sir!
Okay, great. So we're going to complete this lesson on the factors that affect rotational acceleration. And you might recall the formula for Newton's second law, regular style. Regular style, it's F net equals m times a. But if you write that formula rotational style, each one of these terms gets replaced by a different quantity. Matthew, could you tell me a replacement for one of these quantities?
F net is replaced with torque.
Yeah. And Julia, could you tell me a replacement for one of the other quantities? And Kyle, the A, what does that become?
I forgot the name of it. It's like a fish.
Yeah,
Alpha.
Greek symbol alpha for rotational acceleration. And if you solve that for alpha, that answers the question. What would it be, Dan?
Torque net divided by moment of inertia.
So these are the two factors that affect the rate at which an object is speeding up its spinning rate. One, if you put a bigger torque on that object, it's going to have a bigger angular acceleration. It's going to spin faster and faster at a faster rate. However, if it has more rotational sluggishness, a bigger moment of inertia, then the angular acceleration wouldn't be quite as fast. So this is the formula that we're going to be applying today. Okay, so we already looked at an easier problem where you had a cylinder pulley like this, and there's a rope that's attached around it, and someone's pulling down on the rope with a force of 10 newtons, and the radius of this pulley was given, what did we let that radius be? 0.1? 0.2? 0.2 meters?
Oh, yeah, it's 0.2.
And what was the mass of the pulley? The mass of the pulley was 2.0 kilograms. So if you pull down on this rope over here, it's going to spin this pulley on this axis. I'm trying to draw it three-dimensionally. And by pulling down over here on this rope, you're going to spin this pulley faster and faster. And the question is, what's the rate of the angular acceleration? So we know that angular acceleration depends on two things: the net torque and the moment of inertia. In this particular problem, the net torque is provided by this 10 Newton force. But remember, net torque can be calculated with the whole force times the perpendicular distance. In this case, it's going to be 10 newtons times the whole 0.20 meters. But the rotational mass of a solid cylinder, which they would have to tell you this is, follows that special formula 1/2 mr squared, you don't have to memorize that formula. You're usually given a table with the moment of inertia formulas for the various shapes. Now you can be sophisticated and recognize that this r perpendicular and this r here in the denominator, they're the same r, so you can cancel them out and simplify it. But I'm just going to let it be, and if you substitute in the values here, you get 10 newtons times 0.20 meters, and in the bottom here you get 1/2 the mass of 2 kilograms times 0.20 meters, but that radius in the denominator gets squared. And then if you crunch that out, what did we get yesterday for the angular acceleration? So let's just take a moment to think about what that means. If that object started from rest, and this is the time, and this is the angular velocity, at time 0 seconds, the angular velocity would be 0 radians per second. But if it has an angular acceleration of 50 radians per second squared, after 1 second, how fast will it be rotating around? 50 radians per second. And then after 2 seconds, how fast would it be spinning? 100 radians per second. And after 3 seconds, how fast would it be spinning? 150. It keeps going up by 50. That's what this angular acceleration tells us, the rate at which it's speeding up. It's speeding up by 50 radians per second each second. So that was like our warm-up problem, yes? Then we went on to tackle that harder problem. The problem with the cat pulling on the tablecloth to get the fish tank in order to get the fish and eat the fish. Meow. So this problem usually isn't shown like this. It's drawn more theoretical, like this right here. And this is actually a blast from the past problem. And we calculated the acceleration and the tension in the string of this very problem in an earlier lesson last fall. But now we're going to make it more realistic, and we're going to say that this pulley right here is a cylinder, and it's going to add rotational sluggishness to the system. And what did we say the radius of that pulley was? Oh, I didn't tell you.
0.2 meters.
All right, 0.20 meters, just like before. And what about the mass of the pulley? 2 kilograms? So as soon as you see that additional information was given about the pulley, then you recognize, oh, I got to bring in the rotational stuff. I'm going to have to use Newton's second law of rotational style. Now, the first thing that this leads to is the fact that there's not going to be just one unknown tension force. Now, instead of calling that T, it's more fashionable these days to call it F sub T. But But as soon as you're told that this pulley here has mass and it's a cylinder, it complicates things because now there's going to be two different tensions in the string. In the past, there was only one. In the past, this guy right here was pulling on this guy right here, and there was a tension force like that, F sub t. But this guy here can't pull on this guy here without this guy here pulling back on this one just as hard. So this one here was pulling back with the same tension force, F sub t. And those were equal to each other when we had an ideal pulley, a massless pulley. But now that that pulley has mass, it's more complicated. The string over here turns out to have a greater tension than the string over here. So now the problem looks like this. This mass right here is pulling down on the string, which is, maybe I'll draw this in red, is making this pulley right here spin in the clockwise direction. The string right here is pulling down on that pulley, making it spin in the clockwise direction. So there's a tension force there. F T. And if this object right here pulls down on the string, which pulls that pulley forward, well, it can't do that. It can't pull the pulley down without the pulley pulling up just as hard. So there's your tension force there going up. But now there's going to be two tension forces. So we're going to have to call this FT1. So the vertical part of the string has a greater tension than the horizontal part of the string. Now, the horizontal part of the string this object is being pulled to the right by the string right here. So there's a tension force to the right, but that's FT2. But if this rope here is pulling that object to the right with a certain tension, the other end of that string right here on top of the pulley is going to be holding the pulley back with a tension force of the same magnitude, FT2. There's two FT1s and there's two FT2s. So now, instead of just having two unknowns, the acceleration and Ft, there's actually going to be three unknowns. What is the acceleration? How fast is this accelerating down? Likewise, how fast is this accelerating to the right? And since they're connected by the rope, they're going to have the same acceleration. And that's one question. What is that acceleration? Another question is, what is the tension in this rope on this side over here? Ft1. But now there's also a third unknown, Ft2. How much is the tension up here? In the string that's up top here.
Sure.
Yes?
I have a question. Like, I thought when we did this before, that like the force, the Ft on one side and Ft on the other side were equal.
They used to be. They were,
So now not anymore.
but not anymore.
Okay.
So when we did the problem before, the problem would have stated it was an ideal pulley, or sometimes it'll say it's a massless pulley, well then you wouldn't be given any of this information right here, and then FT down here, FT1, and FT2 over there would have been equal. They would have been just FT. But now that they tell us, oh ho ho ho, you know, this pulley has mass, now there's two tension forces.
Why would, if the FT1s, if they were going equal in opposite directions on both sides, why wouldn't they all just cancel out?
Well, they're acting on different objects. See,
Oh, so it's, okay.
Newton's third law, those action-reaction pairs, they never act on the same object, so they never cancel each other out. So like this object right here is being pulled up. The pulley over here is being pulled down.
Okay.
They're not acting on the same object.
All right, thank you.
Good questions. All right, so we're set up now. We have our scenario here, and we have our three unknowns. Now, if we have three unknowns, guess how many equations we're going to need? 3 equations. So, we're going to have to look at each object individually. We're going to look at this mass right here. We're going to look at this pulley right here. And we're going to have to look at this mass here. And we're going to apply law number 2 from a man named New to each of these 3 objects. You all ready for this?
Dun, 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 dun.
Thank you, thank you. So, here we have these are called free body diagrams because we're freeing the object up from the rest of the diagram. So I'm taking this and I'm freeing it up, free at last. And I'm redrawing it over here, 3 kilograms. And then I'm freeing this pulley up, and I'm drawing it over here. Actually, and then I'm freeing this mass up and drawing it over here. So what I'm going to do is pause the video and ask you guys to think about the forces acting on these 3 objects, and then we'll come back and we'll draw on the forces, and then we'll have to solve for our unknowns. All right, if I draw all the forces acting on this 3 kilogram, we have this tension force to the right, FT2. We have the weight force pulling it down, Fg equal to 30 newtons, if you did Fg equals m times g. And then we have the tabletop underneath, holding it up. So that's an upward normal force. And that would be perfectly holding up the weight, so that would also be 30 newtons. That Fg 30 newtons down and the Fn 30 newtons up, they cancel each other out, and they're not really going to play an important role in this problem. But this Ft2 is. Now the other side of the string is going to be holding this pulley back and pulling back this way with that same exact tension, Ft2. Meanwhile, the other side of the rope over here is going to be pulling the pulley forward, and we know the pulley is going to be spinning faster and faster, so this side of the rope is actually going to pull down with a greater tension force. So we know that this force down here, Ft1, is going to be bigger than Ft2, so I draw it a little bit longer. And then whatever Ft1 is, it's going to be the same on this object. Again, not canceling out because they're acting on different objects. And then this object over here also has its weight force pulling it down. Fg equal to 2 kilograms times 10 meters per second squared, and that would be 20 newtons. Matthew?
So there's no gravity acting on the pulley.
That's a great question. That's very insightful. And for the last minute or two, I've been debating in my mind whether to bring that up. And I was just going to kind of let it slide. But there is. There really is a weight force. That pulley has mass, so it does have a weight force, Fg. And there would have to be like a bracket, like something on the table, some kind of bracket here, you know, holding it there. And that bracket is actually going to be putting like a force on it. So there would be also this complicated bracket force, you know, the force due to the bracket that's holding the pulley. But we're only going to be analyzing the forces that are causing torques. And since both of these forces go right through the center of the pulley, they don't do any torquing. So they're not going to be significant in this problem, but they are there. Bravo for bringing that up. So I'm just going to backtrack here because they are there, but they're not an important role. You know what? I think I'm just going to leave them there. We'll leave them in. But we just know they don't do any torquing.
So we don't have to worry about them.
So we don't have to worry about them.
That's above my pay grade.
So now what we have to do is we have to apply law number 2 from a man named
Ton.
to each of these objects. To the object over here, we're going to apply it translational style because it's going to be going forward along a straight line. So for this object over here, we're going to apply F net equals m times a. And we have to make substitutions in for F net and for m, and then rewrite it with the a. And then for this object over here, same thing. It's going to be going faster and faster straight down. So we're going to apply F net equals ma to that object as well. But for the pulley is not moving translationally, but what is it doing? It's going to be rotating faster and faster. So instead of applying F net equals ma, what formula are we going to be applying in that case, Michaela? Exactly. T net equals I alpha. So I'm going to pause the video again, the recording.
It's on right now?
Yes.
I'm on.
And I'm going to see if you could replace and write substitutions for each of the values of these 3 equations. Okay, so we're back. So let's start with this object over here. If we apply Newton's second law to that, what's going to be an expression for the net force, Manav, for this object over here?
Ft2 equals.
It's just going to be Ft2. Bravo. There's no friction holding it back in this case, so it's just Ft2 pulling it forward. And then, what can I substitute in there for the mass?
3 kilograms.
3 kilograms. And do we know the acceleration? No, that's one of our unknowns. So that there is our first equation. I want to jump down over here to this object right here. Simon, I want to replace F net equals ma for this object.
Simon.
Or Andrew. Andrew.
So who's Simon? It's going to be Fg minus Ft1.
Right, and what's the value of Fg?
20.
So it's going to be 20 newtons minus ft1 equals how much mass?
It's gonna be 2.
2 kilograms. And what about the acceleration?
We don't know.
We don't know it. Bravo. That's our second equation. Whoa. And now we have to apply Newton's second law rotation style for this one here. But remember, we're probably going to be told here that that's a solid cylinder. So what's an expression for the net torque? Zainab?
I said FT1 times 0.2 meters.
FT1 times 0.20 meters forward, yes?
Minus FT2
Minus FT2
times 0.2 meters
times 0.2 meters,
equals 1/2.
1/2,
2 times 0.2 meters squared.
2 kilograms times 0.20 meters quantity squared
And
times
then I know alpha.
times alpha,
Yeah.
right? But instead of writing alpha here, what can we replace alpha with? Mohammed? Yeah, let me think about it. What's the third version? There's SOAR, and then there's VT equals omega R, and then there's A equals alpha R. So if you solve that for alpha, what is it going to be? Bravo, Mohammed.
Yes, sir.
A over R. But what is R? The 0.2. Bravo. So this here is our third equation. And actually our physics now is done. And now it's just a math problem, simultaneously solving a system of 3 equations for 3 unknowns. So take a break. I'm going to write out how to solve 3 equations for 3 unknowns. And then when you come back, you can take a look and we'll compare answers.
Yes, sir.
All right, how's everyone still feeling? So we're solving this system of equations. We're using Newton's second law, F net equals ma, and second law rotation style, net torque equals I alpha, to solve for 3 unknowns: the acceleration of the system and the 2 tension forces. Now, what I did was I copied these 3 equations with the 3 unknowns. But once you write it out with units, you could drop the units the next time you write it out. And some people find it like a huge aid, a huge simplification to rewrite it without the units. So I just dropped all the units to make it look less complicated. So I copied these formulas and I called them equations 1, 2, and 3. Equation 2 was the torque one, but all kinds of things cancel out. See if you can follow me on this. At first, this 0.2 right here canceled out with one of those 0.2s, so that got rid of the square. And then each term had another 0.2 left. So you could divide out 0.2 from each term. So that cancels out this 0.2 and this 0.2 and the remaining 0.2 that was left after we got rid of the square from before.
How did the 0.2 under the A get canceled out?
The 0.2 under the A wiped out one of these 0.2s
Yeah.
because it was squared. So this one got rid of one, so I just crossed off the square.
Oh, it's
Oh,
canceled.
so
It
it's
was double
0.2
canceled,
now.
basically.
Right, yeah.
No, it's just 0.2 now.
Now it's just 0.2.
Why is there?
I thought I thought you crossed out all the 0.2s, and then the other 0.2 canceled out the square.
Oh, you
Well-
crossed out the 0.2
Well,
with the...
Whichever way you want to do first, it doesn't matter. Like, I could have crossed out 0.2 from each term,
And I take it out the square.
and if I crossed out one of them, what would have been left?
0.2.
0.2, and then how do I get rid of that sucker?
The other.
With the one over here.
Oh, so they're all canceled out.
They're all canceled out.
All right, perfect.
And then notice 1/2 times 2, they cancel out. So that second equation simplifies down hugely to ft1 minus ft2 is equal to a. So I have 3 equations now with 3 unknowns, a, ft1, and ft2. There's a variety of different ways of solving 3 equations for 3 unknowns. I'm just going to show you my approach. What I recognize is if I take this ft2 right here, and I substitute in the value for this ft2, my second equation will only have an ft1 and an a, and my third equation has an ft1 and an a. So I would immediately reduce the problem to 2 equations and 2 unknowns. So I'm going to substitute equation 1 into equation 2. And when I do that, equation 2, this equation right here, it's going to become ft1 minus, but instead of ft2, what am I going to write there? 3a equals a. So that's my new equation 2. This was my original equation 2 up here. And this is my new equation 2. And then I'm going to just plainly rewrite equation 3. And when I rewrite equation 3, I have 20 minus ft1 equals 2a. And then I'm so psyched because I just made a 3 equations, 3 unknowns into a simpler 2 equation, 2 unknown problem. And then again, there's many different ways of solving 2 equations for 2 unknowns. I like the approach where you add the equations together. So if I add the left 2 sides, it has to be equal to the right 2 sides. And I could have brought that, oh yeah. I might as well just bring that over. So let me rewrite this one over here. That's going to be what?
6a.
ft1 equals to 4a. And now I'm just going to recopy the one underneath it. 20 minus ft1 equals 2a. Ruth, that was a good suggestion. It's going to make it easier now. If I add the left 2 sides, what's ft plus 20 minus ft1?
20.
Just 20. And then I have to add the right 2 sides. And now, woo! I'm down to 1 equation, 1 unknown. Oh, feels so good to be back to 1 equation, 1 unknown. That's so solvable. And I just have to divide both sides by 6. So the acceleration is going to equal 20 divided by 6. And what is 20 divided by 6, Jamie?
3.3.
3.3.
Isn't 3.3 repeating?
It is, but I think we only had 2 sig figs in the original problem.
Okay.
So that was one of my 3 unknowns.
So we just plug it back into the second equation now?
Now we could plug it into the second equation, bravo. So now ft1 is going to equal 4 times a. I'm going to use my non-simplified value. So I'm going to use the 20 over 6 value because that's what a was before we rounded it down to 2 sig figs. So 20 over 6. And then what does ft1 become? 4 times 20 over 6. How much? 13.3. Woohoo! Got my second unknown. And then finally, I can go back to the first equation, ft2 equals 3a. And I'll squeeze that right in here. What was that equation? ft2 equals 3a.
Is that right?
You know, maybe I should just make this smaller.
What's the one below it? ft1 minus ft2 equals.
I'll make that all smaller there. So now, ft2 equals 3 times a, but again, I'll use the 20 over 6, the non-simplified version. So what does ft2 end up equaling? Yeah. Looks like we made it. Woo! Yeah.
Did it.
We did it. So we found the tension in the vertical part of the rope, and that was a greater tension, 13.3 newtons. We found the tension in the horizontal part of the rope, 10 newtons, and we found the acceleration of the system, 3.3 meters per second squared. So that's from solving these 3 equations, which came from Newton's second law, both translational and rotational. And that all came from this problem here, when you had a real pulley that had mass and its own rotational sluggishness. So, in conclusion, what are the 2 factors that affect angular acceleration?
Net torque. Yeah, right.
And
Moment of inertia.
moment of inertia. Okay, all done.
Turn it off.